I am Rajesh Sangilda, Assistant Professor, Department of EEE, Vignan Nirla Institute of Technology and Science for Women. In this lecture, I am going to explain about transient analysis of RL circuit when it is excited by DC supply. Now, before that, what do you mean by the first order circuit? So, see, the circuit that contains only sources and resistance and inductance are called RL circuits. And the circuits that contains source, resistance along with capacitor are called RC circuits. So these RL circuits and RC circuits are called these first order circuits because if you write the differential equations, KVLs or voltage equations for those circuits, we will be getting the differential equations of first order. So that's why these are called first order circuits. Now let us see the transient response of RL circuit with DC supply. So we are going to use the differential equation approach. So see the circuit, here we are having a RL circuit which is excited by DC source of V volts connected through switch. Current in the circuit is I. Now let us apply KVL. So before applying KVL, now suppose the switch is closed at t equals to 0. So as the switch is closed at t equals to 0, now let us apply KVL for the circuit. Let us derive the expression for that response of I in the circuit. So for that first we need to apply KVL. So applying KVL gives V minus R into I minus L into di by dt equals to 0. From that we can get V, of course this is a linear differential equation of first order. Now from that equation we can write Vs equals to R into I plus L into di by dt, which can be further modified to Vs minus R into I equals to L into di by dt. Now you can rewrite that as 1 by L into dt equals to 1 by Vs minus Ri into dt. Of course it is of di. Now integrating both sides gives in the left side 1 by L integral 0 to t dt. Now in the right side it is of the integral 0 to I or I of t 1 by Vs minus R into I di. It is of di. Now so integrating the above equation gives 1 by L into t limits of 0 to t equals to ln of Vs minus R into I by minus R. Integration of that 1 by Vs minus R into I gives ln of Vs minus R into I by minus R with limits 0 to I. Of course it is of 0 to I of t. Now in the left side minus R by L into t minus 0, putting the limits. In the right side ln of Vs minus R into I of t, upper limit of I of t minus ln of Vs. So putting 0 lower limit in the place of I gives the second term ln of Vs. Now simplifying the equation gives ln of Vs minus R into I by Vs equals to minus R by L into t. Now simplifying the above equation gives Vs minus R into I of t. Taking this ln to the right side, it becomes e power minus R by L into t. Now I of t, from that equation by writing the I of t becomes Vs by R into 1 minus e power minus R by L into t. So if you draw the waveform for this response I of t, so if you put t equals to 0 initially when the switch S is closed at t equals to 0 in the equation, then it becomes I of t equals to 0. See, the waveform starts at 0 as the t goes on increasing. Finally at t equals to infinity, if you put the t equals to infinity in the equation, then current becomes Vs by R. So which will be the steady state. See the waveform, finally it is reaching to steady state value, that is Vs by R. Now finally expression is I of t equals to Vs by R into 1 minus e power minus R by L into t. I can write that e power minus R by L into t as e power minus t by L by R. That L by R I am taking it as some time constant tau for this RL circuit. So finally for RL circuit the time constant is tau equals to L by R. So how can you define this time constant? If you see the previous response curve, it is starting from 0 of current, finally it is reaching to steady state value Vs by R. So now here the time constant means it is the time taken for the response, here response means I, to reach the 63.2% of its final value. So 63.2% of its final value means here Vs by R. So that time is set to the time constant. If you put t equals to tau in the equation, then you will get this I of t as 63.2% of means 0.632 of Vs by R. Now see the different conditions of time constants. At t equals to 0, if you see the current, it will be 0. from that waveform. If you put t equals to tau, then I will be 0.632 of V by R. If you put t equals to 2 tau, then current will be 86.5% of V by R. Likewise, so on. Finally, at t equals to 5 tau, if you see the current, that is response, which will be 99.3% of Vs by R. See here, if you put t equals to 5 tau, you are getting the response as 99.3% of Vs by R means steady state value. Almost it is reached to steady state value. So that means theoretically, if you want to take the infinity instant, final instant, you can take it as t equals to 5 tau instant, as at 5 tau, your response is almost reaching to 99.3% of final value. So we can take that instant as final instant. Now, if you write the expression for voltage across the resistance, then it will be VR1 equals to simply current into resistance. So already we got the expression for I. So into R, that is Vs by R into 1 minus e power minus t by tau, or e power minus R by L into t. Similarly, if you want to write the expression for voltage across coil, that is inductance, then it will be VL equals to L into di by dt. Already we got the expression for I of t. So L into d by dt of this current equation gives the voltage across inductor as Vs by R into Vs minus Vs by R into R1 into 1 minus e power minus R by L into t. Now, if you draw the waveforms for these voltage across resistance and voltage across inductance, see the waveform. Voltage across resistance start in the initial instant at t equals to 0, it is 0, voltage across resistance is 0. Finally, the voltage across inductance resistance becomes the supply voltage. Finally, it is reaching to Vs. If you see the voltage across inductor, initially it is 0, total supply voltage appears across inductor. Finally, as the t approaches to infinity, means after long time, your voltage across inductor becomes 0, because the inductor acts like short circuit after t equals to infinity, because the supply is of DC supply. So if you see the expression for decay of current, initially inductor starts charging. After that, if you see the decay of current in the circuit, it can be written as Vs by R into e power minus R by L into t. Now here the students can be asked a question, define time constant of RL circuit. Just now we have explained that time constant of RL circuit is tau equals to L by R, and the definition is it is the time taken for the response to reach the 63.2% of its final value. Similarly, current through an inductor cannot change instantaneously. Justify this. So students can be asked this question also. Now answer for this question is, if you see the voltage across inductor is VL equals to L into di by dt, if the current changes instantaneously within 0 time, then this voltage becomes infinity, but which requires an infinity amount of power, which is not feasible and which is not practically possible also. For that why inductor does not allow sudden changes in current. Now, if you take an example based on this transient analysis of RL circuit, let us take an RL circuit of R value 30 ohms, of L value 15 henries, and supply is of 60 volts DC supply connected through switches. Now you are asked to determine the current I and voltage across resistor and the voltage across inductor. Now see here, so by applying KVL for the circuit, L into di by dt, voltage across inductor is 15 into di by dt plus 30 into I, R into I equals to 60. So this equation gives di by dt plus 2 into I equals to 4. So solution of this equation becomes, if you use the differential equation approach and solving the complete solution for this current, gives I equals to c into e power minus 2t, which is complementary function, which gives transient response, plus 2, which is particular integral, which gives steady state response. Now at t equals to 0, switch S is closed. So in order to get this value of arbitrary constant c, we need to go for initial conditions. For that, at t equals to 0 is the initial instant of switching operation. So at t equals to 0, as the inductor does not allow any sudden change in current, the current will be 0. So putting t equals to 0, I equals to 0 in the above equation gives c equals to minus 2. So finally your current expression will be I equals to 2 into 1 minus e power minus 2t amperes. So now the equation for voltage across resistance can be written as VR equals to simply I into R. So I means 2 into 1 minus e power minus 2t into R means 30. So finally VR equals to 60 into 1 minus e power minus 2t. If you see the voltage across inductor, which will be L into di by dt, where L is given as 15 into d by dt of I means Just now we got it as 2 into 1 minus e power minus 2t. So solving this gives 30 into 2 means 60 into e power minus 2t. Now so far we have used the differential equation approach to get the complete solution for the response in case of RL circuit when it is excited by DC supply. Now let us use the Laplace transform approach to find out the response in the RL circuit. For this, the total procedure of using of Laplace transform is: first develop the differential equation from the circuit after a switching operation. Next apply the Laplace transform for the differential circuit. Then algebraically solve for the solution of the equations. Now apply the inverse Laplace transform in the final step. Then you will get the response of RL circuit which is excited by DC supply. Now let us see the transient analysis of RL circuit using Laplace transform approach. So let us take the RL circuit connected to DC supply through switch of S. Current in the circuit is I. So now first switch S is closed at t equals to 0. Then apply of course if the assumption is inductor initially it is not having any charge. It is unenergized. Charge means energy here. It is unenergized. There is no energy stored in the inductor initially. It is the assumption taken. Now by applying KVL for the circuit after closing the switch at t equals to 0. So after t greater than 0 means after closing the switch, if you apply KVL, Vs equals to I into R plus L into di by dt. Now by applying the Laplace transform for the above equation, Laplace transform of DC supply of constant Vs volts is Vs by S equals to I R into I of S plus L into Laplace transform of derivative. It becomes S into I of S minus S into minus I of 0. Here initially there is no current flowing through inductor, so it is taken as 0 minus 0. Now simplifying the previous equation gives Vs by S, I of S is taken as common R plus SL. Now from this I of S becomes Vs by S into R plus SL. Now taking the partial fractions of above equation gives Vs by R into 1 by S minus 1 by S plus R by L. Finally if you apply the inverse, of course this is the final Vs by R into 1 by S minus 1 by S plus R by L. Finally if you take the inverse Laplace transform, it becomes Vs by R into inverse Laplace transform of first part becomes 1 and inverse Laplace transform of second part becomes e power minus R by L into t. So finally it will be I equals to Vs by R into 1 minus e power minus R by L into t. So this is the same expression which we got when we are using the differential equation approach. So we can use either of the approach to get the response in RL circuit when it is excited by DC supply. Now here is the response curve for I of t.